Hi, Physics 1. This is Mr. Janowski. This is the first part of the Chapter 6 slides. So, do now questions. When does mechanical equilibrium occur? Use a sigma in your answer. So, remembering back to Chapters 2 and 3, mechanical equilibrium occurs when sigma f equals 0, when the sum of the forces on an object equals 0. So, question 2, describe the motion of an object that is at rest and in mechanical equilibrium. So if it's at rest and there's no net force in it, it is going to stay at rest. Question 3, describe the motion of an object that is moving and in mechanical equilibrium. Well, this one is going to move in a straight line with a constant speed. So in questions 2 and 3, you have mechanical equilibrium, the sum of the forces is 0, and the object's motion doesn't change. If it's not moving, it continues to not move. If it is moving, it moves straight line, constant speed. Questions 4 and 5 are similar questions, only this time the thing is not in mechanical equilibrium, which means the sum of the forces is not 0. So what happens to an object that's at rest but not in mechanical equilibrium? It's going to start to move. And how about if it was already moving and not in mechanical equilibrium? So the sum of the forces is not 0. It's going to change its speed and or its direction. It's going to accelerate. It might speed up, it might slow down, it might change direction, or it might change direction and speed up or slow down. But yeah, its motion is going to move. So, like I said, this is Chapter 6. Chapter 6 is Newton's second law. Chapter 7 is going to be Newton's third law. And we will spend a lot more time doing Newton's second law than we do doing Newton's third law because there's a lot more math you can do with it. So thinking back to chapters 2 and 3, we started talking about forces. A force is a push or a pull, and forces change an object's motion. So the bullet points there, that's about Newton's first law. How does an object respond if the sum of the forces on it is 0? That's the first law. So remember, the symbol for force is almost always going to be a capital F, and you're going to need subscripts because there are different kinds. I try to say kind and type at the same time. There are different kinds or types of forces. You might have F sub g for the force due to gravity, which is more commonly called the weight. You might have a normal force. When two things are touching each other, there is a normal force, normal meaning perpendicular between them. Or you might have different people, Alice, Billy, and Charlie, putting forces on something. So in these problems, there will be, many times there will be several forces. Use the subscripts to keep the forces straight. You can't just call them F because there's going to be too many of them, and you have to keep track of them somehow. And the most common unit for force is the Newton, written as a capital N. So, it's science. Use the SI unit. Use Newtons. So here are some common forces. I'm not going to spend any time here because we'll go over these forces, more eventually when we need them. One by one, we'll learn them again. Weight, normal force, friction, kinetic friction or static friction, and tension. So forces, of course, are vectors because they have magnitude and direction. Some things are only scalars. Your mass, for example, is only a scalar. It only has a size. Your mass does not have a direction to it. Your weight, which is a force, is a vector because your weight has a magnitude and a direction. Your weight, the force due to gravity on you, is down towards the center of the earth. So forces are vectors because they have magnitude and direction. You can have a 100 Newton force directed up or down or left, right, east, north at 30 degrees above the horizontal, etc. So 30 degrees above the horizontal. So just to preview this idea, sometimes our forces will be ugly vectors. And just like last chapter, how do we handle ugly vectors? We do step 0 to them, and we find their pretty components. And then we deal with the pretty components because we would rather do that. So here is La Pulga Atomica, Leo Messi, the atomic flea. So Messi is going to kick a football, and he's going to kick a bowling ball, and he's going to apply the same amount of force to each of them. So the bowling ball's motion is not going to change as much as the football's motion is going to change. So why is this? This is because the bowling ball has more mass, and mass is a measure of inertia, and inertia is laziness. It is reluctance to changes in motion. So both of those objects have mass. They're both sitting there. They're both lazy. Neither one of them wants to move. The bowling ball, having more mass, has more laziness. It is more reluctant to move. So if he puts the same amount of force on both things, the bowling ball changes its motion less. And after we looked at this slide, I went into my whole spiel about how the most important thing you will learn in physics all year, I promise I won't teach you anything more important than what I'm about to show you, is this idea. F equals ma. This is Newton's second law of motion. Force equals mass times acceleration. Such a simple, elegant, beautiful little formula, and yet it explains so much. Pretty much the only thing that's going on in the universe is forces are accelerating masses. Such a wonderful idea. So, coming back to Leo Messi, he kicks the football and the bowling ball with the same force, and now I'm giving you extra information. I'm telling you that the bowling ball has 16 times the mass of the football. So how will their accelerations compare? Well, if F equals ma, that means A equals F over m, which means the football is going to have 16 times the acceleration of the bowling ball, because they both get the same force, but in the case of the bowling ball, you're dividing by 16 times as much mass, so the bowling ball's acceleration will be 1/16 that of the football. And that is equivalent to saying the football will have 16 times the acceleration of the bowling ball. So I gave you a couple problems to do. Three, a couple and a half of problems to do. So yeah, first one, what force is required to accelerate a 50 kilogram mass at 2.2 meters per second squared? Yeah, you want to know F, so plug in M and A, do the math, and you get 110 newtons. The second question, what would be the acceleration of an 80 kilogram mass experiencing a force of 120 newtons? Well, we're trying to solve for A, so start with F equals ma, divide both sides by m, and you end up with A is equal to F over m. Plug in your numbers, and you get 1.5 meters per second squared. And then finally, an object is accelerated at 9.8 meters per second squared by a 735 Newton force. What is the object's mass? We're solving for mass, so divide both sides by A, and you end up with m is equal to F over A. Plug in your numbers, and you get 75 kilograms. So these questions, just three little demonstrations of how you use Newton's second law. Fairly straightforward in this case. The problems will get harder, I promise. But yeah, for the first part of this chapter, this is all you needed to learn. So that's it for this part of the slides. Hopefully you found that helpful.